Let's get started for this semester's very first seminar, and welcome back, everybody. So today we have Dr. Krishna Balasubramanian from the Department of Statistics at UC Davis. And his research focus is on addressing inferential and computational issues arising in statistical problems. And today he will tell us something about the non-asymptotic aspects of sampling from heavy-tailed distributions via transformed Langevin Monte Carlo. Okay, and let's welcome our speaker. Please go ahead, Dr. Balasubramanian.
Yes, thanks. This is joint work with EA, who is one of my students in UC Davis Math, and Murat Erdogdu, who's a friend and a collaborator from Toronto. And the papers, as of now, titled Heavy Tail Sampling Were Transformed ULA, and it will be archived soon, hopefully in the next couple of weeks. All right, so here's the outline of my talk today. So in the first part, I will introduce some basic results about like diffusion-based sampling and highlight some of the issues, theoretical issues, more specifically non-asymptotic issues associated with existing results. And then I will summarize about in more careful detail. I'll summarize about Langevin diffusions and the results, and then present finally our results. Right. So I guess I'll keep the first part of the talk a little bit introductory. For the experts in the audience, I guess some of these things may be clear, but it's good to still get all of us on the same page, I guess. Right. All right, so what's the sampling problem? So we are given a probability measure, so you can just assume it has a density with respect to the Lebesgue measure. So this would be the density. The f function here is typically referred to as the potential function, and it's a function from Rd to R. And z is the normalization constant, and typically it's like hard to compute it, and we just assume it's unknown. So the question now is, can we generate samples from such a probability measure or a density, if you call it so, right? And just to give a motivating application, although I probably don't need to go through this for this audience, but I'll still go through this briefly. So there's something called as Bayesian logistic regression, where you're given n observations xi, yi, where xi are the features in, let's say, d-dimensional space, and the labels yi are binary, 0, 1. And the goal in logistic regression is to estimate this conditional distribution or conditional expectation. So P of y given x, which is assumed to be of this particular form. And in a Bayesian setting, you have to pick a prior over the parameter space theta. And one proposal by this paper is published in Bayesian analysis is to choose like an empirical Bayesian prior where your theta is assumed to be Gaussian with mean 0 and covariance matrix proportional to the inverse of the sample covariance matrix. Right. So in this case, you can just do the Bayes theorem and write down the posterior density, and you will get your target to sample from in this following format. So you have pi of theta is e to the f of negative f of theta, where your f of theta is given by this format, right? So this, you can work it out and see that this is a strongly convex function, f of theta. So in this case, your density pi of theta will be a strongly log concave density, right? So this is kind of like a motivating application, and like there are numerous other applications, like you can do Bayesian deep neural networks, or like you can pick and play with your prior and posterior distribution, and then like there are a lot of possibilities. So the thing that I will be focused on is like the case when this density pi of theta or e to the f of theta is heavy tailed in theta, right? All right, so just to give a very brief history of MCMC algorithms, so one can kind of talk about two generations of algorithms, at least in my opinion. So the first generation is what is called as random walk metropolis Hastings, starting from like 1950s. So the thing here is that this class of algorithms, they don't use geometric information about the target density. So more specifically, they are only based on function evaluations or density evaluations, right? And there's the second generation of sampling algorithms. So this, you can take a look at this book for more details, but the thing with this so-called second generation of sampling algorithms, which are motivated from the statistical physics literature, is that they use the gradient information of the density that you're sampling from, right, as opposed to this random walk algorithms, right? So the most popular among this class of algorithms are the Langevin Monte Carlo. So I will also use the unadjusted Langevin algorithm because, I mean, they call it so also in the literature. So I will interchangeably use LMC or ULA to refer to this Langevin Monte Carlo algorithm. And then there's like the Hamiltonian or kinetic version of this Langevin Monte Carlo algorithm. So the thing with this algorithm is that both ULA or this kinetic version are biased algorithm in the sense that after running it for a finite number of steps, the density that you actually have at hand is not an unbiased, it's kind of biased from the density that you actually wish to sample from, like from the target density, right? So actually, in order to overcome this issue, people have also proposed something called as the metropolis adjustment step, which is called as the metropolis adjusted Langevin algorithm. So after running this Langevin algorithm, you actually do this sort of a metropolis accept reject step, and that is shown to help remove the bias. All right, so now let's move on to some like existing theoretical results about this. Yeah, any questions? Okay, yeah, so just feel free to interrupt me at any point of time with if you have any questions. Okay, so let's move on to the theoretical, some known theoretical results about the algorithm. So so in the earlier days, like from like 1970s to like 2010 or something, people were mostly interested in about like asymptotic properties of your algorithm. So rates of convergence to the equilibrium in an asymptotic setting. But more recently, in like starting from, let's say, 2012 or something, people started looking at more at the non-asymptotic properties of these algorithms. So basically, suppose that you're running the algorithm for k steps, right? So then how far away from your target you are in some meaningful metric that you want to that you have at hand, right? So towards that, there has been a line of work starting from 2012 or maybe 2014 with the work by Arnak Dalailan. So people, so the culmination of that work or the summary of that work is listed in this table, and I'm probably missing a few key references, but these are like what is known about the non-asymptotic properties of the sampling algorithms. So for the metropolis random walk algorithm, assuming that the density is strongly log concave, the number of in order to get epsilon close to your target density in the Wasserstein 2 metric, the number of iterations that you need to run is of this order. So you need to run for d times log of 1 over epsilon. So it's very fast in some sense, actually, under this strong log concavity assumption, right? And similarly for the caveat here is that for this result, you need a stringent warm start condition. So initialization for your algorithm needs to be like, it has to satisfy a particularly stringent condition. So if you have such an initializer, you can do this, but whether or not such an initializer is feasible from practical point of view, that is not well explored, right? And coming back to the second generation algorithms like ULA and KLMC, under strong log concavity, the known rates in Wasserstein 2 metric are of the order d over epsilon square, right? So you're not as good as the random walk, but again, this is without any stringent warm start condition, so it's not a fair comparison. So this holds for any initial distribution, right? And okay, so as I told, for the example that I showed previously, the f is the potential function f was strongly convex, so the density was strongly log concave. Whereas, so this restricts the modality of the density, so it can only be unimodal. Whereas, if you assume something called as log Sobolev inequality on your target density, so we will look at the precise definition in the next section. So under this condition on your target density, Vempala and Bibiciano, they showed that the order of your the number of iterations is of the order d over epsilon squared. So this is a relaxation. So for even more wider class of densities, you can get this order of rate, right? And more recently, my collaborator Murat and a student showed that you can further relax this condition from LSI to modified LSI, which again, I will explain what it is in a second. But so even for this class, you can do this d over epsilon squared rate, or you can get this d over epsilon squared rate, right? And so this is the state-of-the-art result for ULA. And for the kinetic version, again, it's relatively not so well studied as the unadjusted Langevin. So for the kinetic version, only under strong log concavity, your rates improve to, like, it's basically the square root of this rate. So basically you have a root d over epsilon in Wasserstein, right? So this is kind of like the existing results about this sort of diffusion-based sampling algorithms in some sense. So what are the drawbacks of these kind of algorithms, at least in terms of this theoretical rates of convergence? So all of these results require either strong convexity of your potential, or it can only be sub-Gaussian or sub-exponential, so to speak. So your f of x can only be like of the order of norm x, or like norm x to the alpha between, like, where alpha is between 0 and 1. So what happens, or what could you do when your density is basically not of that form? So more specifically, your potential is only growing logarithmically in norm x, right? So one classical example to keep in mind through the rest of the talk is this multivariate T distribution with, say, theta degrees of freedom. So where the potential, the density is of this form, and in this case, the potential is given by this. So basically, you see that's a log of 1 plus x squared. So because the growth of this function is like only log of 1 plus x squared, so if you exponentiate it, the density is supposedly heavy-tailed, right? So what happens, or how do you deal with this class of densities is this is the question that I'd be trying to address in this talk, right? All right, so specifically, as I told, the existing convergence results of this ULA are not applicable to heavy-tailed densities, for example, this multivariate T distribution. So in this work, what we do is we propose a transformation. So in statistics, it's common to transform your random variables before like doing what you want to do, right? So we propose a simple transformation-based approach for sampling from heavy-tailed distributions and give a precise non-asymptotic analysis of their properties, right? All right, so I'm now going to go into some details. So maybe I will take a pause to see if there's any questions. Any questions? Okay, so if not, let me proceed. So what is this Langevin Monte Carlo and unadjusted Langevin algorithm and this kinetic Langevin algorithm, right? So basically, these are all based on diffusion process, which is given by the stochastic differential equation of this form. So xt, xt is the stochastic process where t is the continuous time index, right? So the SDE is given by this form where your f is the potential function, right? And this is the gradient. So this is basically the negative gradient of the potential function. And there's a root 2 times dbt, where bt is basically a standard d-dimensional Brownian motion initialized at origin, right? So the point is that this is a continuous time diffusion, right? So one can show that the stationary distribution of this diffusion is going to be of this format, right? So now if you are able to simulate this diffusion, excuse me, so then you will be able to, after you run it for a number of steps, excuse me, you'll be able to simulate from this target density that you wish to sample from, right? So that's the idea. And because it's based on because this sort of algorithms are based on discretizations or time discretizations of diffusion processes, these are also called as like diffusion samplers in the literature, as opposed to like other types of sampling algorithms, right? So before I proceed, I need to introduce some definitions which are quite standard, right? So between two densities, mu and rho and mu, the Kullback-Leibler divergence of rho with respect to mu is given by this expression here, and this is not a symmetric distance metric, so you need to talk about it as like rho with respect to mu, right? So, and you have something called as the relative Fisher information, which is basically defined in this particular manner. So these are like probably standard definitions that we have seen multiple times perhaps, but I just want to keep all of us on the same page, right? So let me define what log-Sobolev inequality is now, right? So suppose that we say a density mu satisfies a log-Sobolev inequality with some constant c, right? So we say that a density mu satisfies LSI of constant c with constant c if this relationship or this inequality is true, right? So you can more elegantly write this in the form of this definitions that I introduced here. So all you need to remember or keep in mind is that a density satisfies LSI with constant c if the Kullback-Leibler divergence is upper bounded by c over 2 times the relative Fisher information, which is given by this expression here. So this is the thing that you need to keep in mind, right? So your Kullback-Leibler has to be upper bounded by the relative Fisher information times some constant, right? So this looks like some abstract definition, but what's nice about this definition is that it's well known that if your Langevin diffusion is so if your target density satisfies LSI condition, then this Langevin diffusion that I introduced in the previous slide mixes or like it converges to the equilibrium exponentially faster, where the rate is given by this log-Sobolev constant c, right? So this is why it makes sense to introduce this LSI definition and talk about this, right? So for us from a statistical perspective, what is this class of densities that satisfy this LSI condition? So it's precisely a class of densities that are sub-Gaussian. So if you can show that, so firstly, any strongly log concave density would satisfy the LSI condition. So this result would apply to any strong log concave density. And a necessary condition is that if a density satisfies LSI, then it is indeed sub-Gaussian, right? So only sub-Gaussian light tail densities fall under this, satisfy this assumption, and this result could be applied only to those class of densities, right? And this is exponential convergence to equilibrium. So there's a slight modification of this LSI inequality proposed by Villani and Toscani. So basically what we need to think of in terms of modified LSI is that so if you So the left hand side is still the same, the relative, the KL divergence. In the right hand side, so in the previous case for LSI, you had just the relative fish information, but now you introduce a parameter delta between 0 and 1/2, and you just trade off a little bit of this relative information with some quantity, which is basically like a moment of your density, right? So you have 1 minus delta of this relative fish information, but then you have delta of this the moment, right? So this relaxation allows for slightly more broader class of densities, which are not sub-Gaussian, but sub-exponential densities would satisfy this sort of a condition, right? So for example, densities of this form, you can show that it satisfies this MLSI condition, right? So this, along with this MLSI condition, you need something called as a dissipativity condition, which is given by this. So the intuition behind dissipativity condition is that you can be non-convex inside, or you can be multimodal inside a ball, but outside a ball you have to be just like just decaying fast rapidly, right? So for example, you can have potentials of this form which would satisfy this sort of a dissipativity condition, right? So the reason why I introduced this MLSI and dissipativity condition is that if your density is density satisfies this MLSI and the dissipativity condition, one can show that it is polynomially ergodic, right? So if you in comparison for the densities that satisfy this LSI condition, your diffusion is exponentially ergodic, whereas for this class of densities it's only polynomially ergodic. So you see, if you want, so in a more statistical language, if you want to go from sub-Gaussian to sub-exponential, which is like slightly heavier tail than sub-Gaussian, your exponential ergodicity already becomes polynomial ergodicity for the continuous time diffusion. That's the key takeaway from a statistician's perspective here, right? So this is the case for the continuous time diffusion. Of course, the continuous time diffusion is not the one we practically implement on a computer. So you need some sort of a discretization for these continuous time diffusions. So the standard discretization is what's called as the Euler discretization. So if you take your density that I showed here, I mean the diffusion that I showed here, and apply the standard Euler discretization, you would end up with this algorithm, which is called as the unadjusted Langevin algorithm, or the Langevin-Monte Carlo algorithm, right? And this is just a Markov chain-based sampling algorithm, right? So your UN is a standard Gaussian vector. So this is still the negative gradient of the potential, and this is just the iterates, right? So as you can see, so suppose that you ignore this Gaussian term for a second. So just look at xn plus 1 is xn minus some gamma times gradient of f of xn. So if you have any background in optimization, so this part is basically just gradient descent, right? So this kind of, so this is the reason why people in optimization have kind of moved or flocked into this area of diffusion based sampling, because they can now they can use all their tools at their disposal to give non-asymptotic guarantees for this sort of sampling algorithms, right? So that's one of the reasons why you see a lot of people from optimization moving into the sampling area, because they can try, with their tools, you can understand a lot about the sampling algorithms as well, right? So as I told in the introduction part, this discrete chain is a bias chain, which means that the stationary distribution of this chain is different from your target. So you have pi gamma, which depends on your step size gamma. So this is the stationary distribution if you run the chain for infinite time, which is going to be different from the pi, which is your target. So different from your continuous time results, in order to give rates for your discrete time results, you also need additional smoothness conditions, right? So for the continuous time results, you only needed curvature sort of conditions like LSI, strong convexity, and all these things are kind of curvature conditions. Whereas for analyzing these discretizations, typically you also need smoothness conditions. So standard smoothness condition is what is called as gradient Lipschitz condition. So if you move from X to Y, your gradient doesn't move much, and it's specifically upper bounded by this constant L, right? So under the assumption that your density satisfies a target density satisfies LSI constant of order C, and your potential satisfies some gradient Lipschitz condition with parameter L. So Vempala and Vibiciano showed that in this KL metric, you have this sort of a result for your discrete chain. So this iterations. So here by rho n, I mean the distribution or the law of the nth iterate of your algorithm, right? So this was shown. So now from this step, you can just pick your gamma. So gamma is a user defined parameter. So you can pick your gamma to minimize the right hand side, and you obtain the complexity that I showed in the table in the introduction, right? So now similarly, you can ask the same question under what happens under the modified LSI condition. So recall that for the continuous time dynamic, if you go from LSI to modified LSI, your ergodicity condition is like it goes from exponential ergodicity to polynomial ergodicity. Whereas for the discretization, it's not the case. So if you assume an additional condition which is like bounding the growth of the gradient, so you tell that your gradient doesn't grow too fast, not as fast, not faster than this rate, like norm x to some zeta. Edogdu and Raza Hosa Deni, they showed that if your density satisfies modified LSI and your function is alpha dissipative, so these two conditions are required even for the continuous dynamic, and in addition your gradient satisfies this growth condition, then you can get this sort of a result, right? And once again, you can pick your gamma, which is the step size accordingly, to minimize the right hand side, and you will end up with the rates that I showed in the initial part of the slide, right? So basically, this is a fine distinction to keep in mind. So even though your continuous time discretization, continuous time diffusion is not exponentially ergodic, it is only polynomially ergodic, but actually you don't really need exponential ergodicity of your continuous time diffusion to get like good rates for your discretization. So this is an important thing to keep in mind, actually, right? So to summarize, what's the state of the art with respect to like moving away from like strong convexity, I mean the log concave densities or strongly log concave densities? So there are only these two results which goes under LSI and MLSI. LSI is only applicable for light-tailed, sub-Gaussian light-tailed, and MLSI results are only applicable under exponential light-tailed, sub-exponential kind of things, right? So again, coming back to our motivating example or the illustrative example, T distribution does not satisfy any of these assumptions. So these results are not applicable to like heavy tail densities, right? So now we will introduce the transformation technique. So maybe let me take a pause briefly just to see if there's any questions. right? So if not, let me move on. So basically, this idea has been proposed by this idea has been proposed in a simple form by Johnson and Charles Gare from Minnesota. So the idea is you need to construct a diffeomorphism, which is just a fancy word for like a one-to-one and invertible mapping, right? So this H is a map from RD to RD. So let's say you have a density mu, random vector X which follows the density mu, and you apply this mapping and construct your Y random vector. So basically define Y to be H inverse of X, right? So then you can show, I mean, it's easy calculation to see that the density of this Y random vector is given by this format. And we call mu H as the transform density of mu, right? So we can assume that, okay, so for the rest of the talk, I'm just going to assume that my transformation H or the map H is isotropic. So I'm just going to restrict everything to like the one-dimensional case literally, and everything is through the norms. So basically, I can just work with norms and like extend it to the d-dimensional case, right? So more specifically, I'm going to assume my transformations are given in this particular format for some g, which is like just a real to like positive real number to positive real number function, which is invertible and 3 times continuously differentiable, right? A specific example of this g function. So the point is that once you have this g function, which is just a one-dimensional mapping, you can immediately construct the mapping from RD to RD. That's what I meant, right? So a specific example of this g function was proposed in this paper by Johnson and Gare. This was published, by the way, in Annals of Statistics in 2012. So they gave this specific transformation, so for sake of simplicity, for this talk, I will just present this transformation or work with this transformation. But in our paper, we propose a general class of transformation, so as long as you pick a G from that particular class, anything that I'm going to tell today will still hold true, right? So for concreteness, you can just keep of this sort of a transformation in mind, right? And it's easy to show that if you define your G in this way, and if you define your H in this way, this H will be a diffeomorphism, and it's been proved in this paper. If you want, you can take a look at that, right? So again, just to summarize, in order to get the rates that I showed in the table in the introduction for ULA, we need light tail conditions. So you need like the strong log concavity LSI or MLSI and some smoothness assumptions. So the idea is while these transformations, they are so okay. So the thing with respect to this paper is that they are working in an asymptotic setting. So if you only care about and they only consider the random walk metropolis algorithm, but more importantly, if you're working in an asymptotic setting, a lot of things get washed away. So you can hide a lot of things, important things in like asymptotics. And one important thing which actually matter to us is, so recall that while analyzing the continuous time diffusion and showing the exponential convergence to the equilibrium and things like that, which is an asymptotic style of statement, you don't require any smoothness assumption on the gradients. And we introduce this gradient smoothness kind of condition or gradient Lipschitz kind of condition only for analyzing the discretization and get a non-asymptotic rate, right? So the issue with this transformation map is that on the one hand, if you have a heavy tail density, it will convert it to light tails. But because the density has to integrate to 1, right? So in the process of converting the heavy tails to light tails, you have to move that mass somewhere else, right? So that mass is moved to the bulk, and the bulk then has to become wiggly, like it will become more non-smooth, right? So this really affects the non-asymptotic. I mean, this could potentially affect the non-asymptotic performance if you're not careful, right? And that's where in our paper, actually, we show that if you just do this transformation, you can still get some rates, but those rates are terribly dependent. Like it could even be like exponentially dependent on D because of this sort of not so aligned. I mean, because probably in their paper they only cared about asymptotics, so they didn't really address this issue. But what we are telling is that if you really care about non-asymptotic rates, you need to be more careful in constructing your G function, which also handles this the put some restrictions on the smoothness or the wildness of the bulk, which happens when you convert from heavy tail to the light tail case, right? So that's kind of like the observation here to go from asymptotics to non-asymptotics, right? And yeah, so as I told, they use this sort of a transformation method to establish asymptotic statements about Metropolis random walk algorithm, right? All right, so the good thing about this transformation map is that suppose that your xn and yn are two Markov chains in RD where n is just the integers. So you can think of it as discretized or time discretized algorithms as well. So suppose that xn has density rho n and yn has density nu n. So all of your favorite properties that you want to have for a good Markov chain, they all carry over to it's basically xn and yn are isomorphic. So if you can prove one of these properties for xn, it will also hold for yn and vice versa, right? So irreducibility, reversibility, anything that you want, geometric recursive, polynomial, aperiodicity, recurrence, whatever you want, it's isomorphic with this diffeomorphic transformation, right? And something that we care about is for the metrics that we are considering, which is the general class of phi divergences, of which the things that I showed before are special cases. The phi divergence is also preserved under this transformation. So here rho n is like one chain and nu n is the distribution of the other chain. So if you can show something for this chain, this will also hold for the other chain, right? And here is the definition of phi divergence, but yeah, it's just a generalization of what we discussed before, right? So this really allows us to basically take this. So you're given a true heavy tail density, you apply the transformation and make it light tailed but more non-smooth kind of a density here. So you run your ULA algorithm on this transformed version, and then like you can use the inverse mapping to go back to your heavy tail density. So that's the idea. So formally, so the transformed Langevin diffusion is given by this thing. So here you have FH, where FH is the potential of mu h. So your transformed diffusion, and WT is just a Brownian motion. So your F is your original potential, your FH is your modified or transformed potential. So the stationary density of this transformed Langevin diffusion is pi h. And so this is the discretized version of the transformed potential. So so the only difference is that you have a FH instead of an F. So you just work with the transformed potential function. That's the only difference you need to make. So formally, this is what you have. So you can just do the Langevin step and then do the inverse transformation, right? So now the question is, for what class of densities this method works, right? So we know, okay, so now this algorithm is basically the same as Langevin algorithm or the unadjusted Langevin algorithm with this potential FH. So if you want to leverage the two results that I showed before, we need to show that FH transform the FH potential function satisfies all those LSI, MLSI, and the gradient smoothness conditions and things like that. But this is the transform potential. So what are the original conditions? I mean, what are the conditions on the original density which is given to us, or the original potential which is given to us, so that after transformation, this potential satisfies all those LSI and smoothness conditions. So that's the question we need to address, right? So I'm going to introduce now a list of technical assumptions, but keep in mind that the multivariate T distribution that I have been talking about as an illustrative example, one can show that everything that I'm going to show in the next few slides, you can verify it for the multivariate T distribution explicitly. Although it's just tedious calculation, you can verify it, and we have it in the paper. So you can look it up on the paper if you're curious, right? So again, as I told, I'm just going to assume f is isotropic. So whenever I say f of x is rd to r, if it is isotropic, I can just think of it as f of norm x. So I just think of it as a one-dimensional function. So again, this is done.
We'll have like 5 minutes left.
Yeah, I'm on time. Yeah.
Cool.
Okay. So this is done again only for simplicity. So this is this is one of the conditions that your original potential needs to satisfy. So what roughly this is telling is that your gradient shouldn't decay so fast, right? So or your Hessian shouldn't decay so fast, right? So basically that's the style of conditions that all of the things that I'm going to introduce next will be of the form of, right? So what we can show is that if your original density satisfies this condition, the transform density will satisfy LSI, right? And again, I have a condition for the analog of the smoothness part. So here again, this is an upper bound on like the first and second derivatives of your f, right? So under this condition, you can show that your potential function fh1 is gradient Eclipses, right? So now you have LSI, you have conditions for your transform potential to satisfy LSI. You have conditions for your transform potential to satisfy gradient Eclipses condition. So then you can apply the one of the previous results that I showed and get a similar result for your heavy tail potential. And because of the fact that these two chains are isomorphic and the fact that the phi divergence is preserved, whatever you show for this y chain will be true for the x chain. So I directly write the result for the x chain, right? So the details are not important. The thing to keep in mind is that this form of the expression is basically of the same form as what we had before for the LSI condition, right? So you can pick your gamma and then get like d over epsilon squared kind of a rate, right? And now we can derive similar results for the modified case. Again, just the expressions are complicated, but let me get back to this assumptions in a minute. Under this setting, you can show that pi h1 satisfy the modified LSI, and similarly under this sort of restriction, you can show it satisfies dissipativity and the gradient growth conditions and things like that. So at the end of the day, you apply, you combine our assumptions and the previous result, and then you get a same rate for your the transformed ULA for heavy tail sampling, right? So again, I want to make I want to emphasize this remark. So these are not some obscure conditions that I just cooked up, right? So I want to convince you that it's actually a meaningful thing in the time that I have left. So you give me any potential and I can verify those conditions for you, and specifically multivariate T distributions, you can show that with some calculation, right? And okay, so now this looks a little bit ad hoc in a way, right? So I mean, one way to do is as what I told you, give me one specific heavy tail density, and then I can verify that for you, right? But that's not good. I want to find a general characterization of these assumptions that I'm talking about, like A1, A2, A3, A4, A5, right? So what we show in the paper is that if your density satisfies our condition A1, A2, A3, then it also satisfies something called as the weak Poincare inequality. So let me go to the weak Poincare inequality. So the details again are not important. So now here I have listed something called as the Poincare inequality, super Poincare inequality, and weak Poincare inequality. So I've listed them in a particular order because, so previously I introduced something called as the LSI condition and the MLSI condition. So you can think of this as like extensions of those conditions which allow for heavier and heavier tails, right? So basically the LSI condition is kind of like sub-Gaussian tails. The MLSI condition is kind of like sub-exponential tails, and Poincare is kind of also like sub-exponential tails. But super Poincare is like, it allows for even more heavier tails, like polynomial decaying potential. I mean, the logarithmic decaying potential up to some factors. And weak Poincare is like even more heavy tail. So basically, this hierarchy that I'm talking about is it exactly characterizes the amount of heavy tailedness that is allowed. And more specifically, you can show that if your degrees of freedom of your T distribution is above a particular threshold, it satisfies Poincare inequality. So for that, so we know that for T distribution, if the degrees of freedom is small, then the smaller the degrees of freedom, the heavier the tail is, right? So you can have this control in the degrees of distribution, and then you can translate the notion of heavy tailedness to the fact that your density satisfies one of these three inequalities. So the lower the theta is, your density won't satisfy Poincare and super Poincare, but it will satisfy weak Poincare, right? So that kind of a hierarchy exists. So what we have showed is our assumptions A1 up to A3, they equivalently characterize this weak Poincare. So if our density satisfies our if your density satisfies A1, A2, A3, it has to satisfy weak Poincare, which is like the heavy tailed version of your Sobolev inequalities and Poincare inequalities, right? So for future work, so again, the details of this relationship are all in my paper, but I kept the first part a little bit introductory to address the students as well as requested. So I couldn't go into the details, but I'd be happy to talk about this if you're interested in more in through email or something, right? And for future work, we want to interpret this optimal these maps or these transformations through some optimal transport language, and maybe find like if there are better ways of constructing these maps, or like give some more intuition towards. So the way Johnson and Geyer came up with their map is again through ad hoc procedure, at least I guess. And the way we are doing it also, like just sit down and ad hoc through like some creativity or ad hoc procedure construct the map, right? But is there a mathematically principled framework for constructing this transformation map? Is the question that I'm interested in, right? Right. So I will end my talk here, and I'll be happy to take any questions. Thanks.
Okay. Thank you, Krishna, for a very nice talk. I guess we will only have limited amount of time for questions. Maybe one quick question. If you want to ask a question, please just unmute yourself.
I guess I have a quick question, if I may.
Yeah.
So you just said that the assumptions imply the Poincare inequalities.
Yeah.
Is that the correct direction that you want? Like just showing that the distribution satisfies inequalities also itself imply the assumptions that we need?
Yeah, so actually this is a part of the future work. So ideally I would want the other direction as well.
Okay.
Right. So if my density satisfies weak pointer inequality, then I need to show that this assumption is also satisfied. Right. So that's the direction that we want. So right till now we are not able to show that, and that direction is invariably the hard part in all the sort of like functional inequalities and things like that. But having said that, what we can do, so this is where this future work comes in. So the question more specifically is that suppose so my target density satisfies weak pointer inequality. After transformation, I need to satisfy LSI. Can you construct such a map through this optimal transport approach? Right. So that's that. Then you don't need this particular map that I'm talking about. You can use that other map, and that would also work. So that's the kind of questions that we're interested in now.
Okay, thank you.
I hope that answers the question.
Okay, great. Let's end today's seminar here, and let's thank again for our speakers for a very nice talk.
Thanks. Yeah.
Thank you.
I'd be happy to take any questions through email as well.